AP Chemistry, we're moving into Unit 10, Equilibrium, a new unit, and we'll be spending the week before Thanksgiving on this unit. So what is equilibrium? Equilibrium is the final state of a chemical reaction in which the concentration of reactants and products remain unchanged. Some chemical reactions run until all the reactant has turned to products. So you see the reaction down below, AB goes to C. And at the beginning you have only reactants and no products. By the end of the reaction, all of the reactants A and B have turned into products C. That's generally the way we've thought of chemical reactions as occurring. They start off entirely as reactants, they go all the way to products. Reactions that move only from reactants to products are called irreversible reactions. And they have an arrow pointing from left to right. Most reactions can move both from reactants to products and from products back to reactants. So these reactions are called reversible reactions and are shown by a double arrow. So there is the initial state is 100% reactants and 0% products. By the end of the reaction doesn't go all the way to products. By the end, it may find a happy place where it's 25% reactants and 75% products, and it just kind of stays right there. Unless you change the temperature or the pressure or the concentration of the solution, it'll just stay right there. But given the initial conditions that you gave it at the beginning for temperature, pressure, and concentration, it's going to settle right there, let's say at 25 for reactants, 75 for products. Now, let's say you took that same exact reaction, same conditions, but you started off with 90% products and only 10% reactants in the container. Everything else is the same. By the end of that reaction, you'll end up at the same equilibrium, 25% reactants and 75% products. So there's a happy place that under those conditions, the products and reactants find a nice, happy balance where they're happy to stay, and they stay in that state. In the reaction above, it doesn't matter whether the reaction starts with 100% reactants, that's A plus B, and 0% products, or with 10% reactants and 90% products. In both cases, the reaction will stop when there are 25% reactants and 75% products. This is the equilibrium for the reaction. A reaction at equilibrium is in a state of dynamic equilibrium. Dynamic equilibrium means that the reaction continues to move back and forth, but it does so at equal rates. So here's a simple little example. Let's say in room A you have 12 students and room B has 7 students. Now 5 students move from room A to B and 5 move from B back to A. Then 2 move from A to B, and 2 move from B back to A. Room A ends up with 12 students again and B with 7 again, even though the people move back and forth and there might be different people in the 2 rooms. So they're in a state of equilibrium, but still they're moving back and forth. They're just doing so at equal rates. That's what dynamic equilibrium means. It means the reaction can go in both directions, and it does, but it goes at the same rate in the forward direction as it does in the backward direction. So this is dynamic equilibrium. The equation used to measure equilibrium is called the law of mass action. We often just simply call it the equilibrium equation, but the formal name is law of mass action. So here's an example of a law of mass action for a hypothetical reaction. 2A plus B produces C plus 4D, and that's a reversible reaction. It can go in both directions. The law of mass action for this reaction is Kc equals concentration of C to the first, concentration of D to the fourth, over concentration of A to the second, concentration of B to the third. So we'll break that down to understand what that means. Kc is called the equilibrium constant. And it's the equilibrium constant specifically for concentrations. That's really what the C stands for. So K is the equilibrium constant. C means for a concentration, as opposed to several other types of equilibrium constants that we'll talk about. The exponents on the concentration of each substance is the coefficient of that substance in the chemical reaction. Equilibrium constants have no units of measure, so please remember that. Generally, the equilibrium constant indicates how far the reaction has moved from reactants to products. So if you take that equation again, if products are much greater than reactants, then Kc will be large. So large Kc, if you have a large fraction of the is products and a small fraction is reactants. So the reaction is gone largely from the left side over to the right side, from the reactants over to the products. If the reactants are much greater than products, then the Kc value will be small. So small Kc means you have a small fraction that went to products and a large fraction that remain as reactants. So here's an example. A sample of hydrogen and iodine are mixed in a 1 liter vessel at a temperature of 430 degrees centigrade. Once equilibrium is reached, it is determined that 2.5 moles of HI, 0.25 moles of H2, and 0.5 moles of I2 are present. What is the equilibrium constant Kc of the reaction at this temperature? So again, temperature is just simply setting the conditions that they're not going to change. As long as the temperature stays the same, then this equation works. So there's the reaction. So substituting the number values, that is the law of mass action for that reaction. So convince yourself of that. The 2.5 moles of HI is on the top. That's the product. That's on the right side of the reaction. And since it has a coefficient of 2, you put that in the exponent. On the bottom, on the denominator of the law of mass action, you have H2. It has a coefficient of 1, so it's simply 0.25 to the first power. And then you have 0.5 moles of I2, and that has a coefficient of 1. I2 has a coefficient of 1, so that's 0.5 to the first power. And you just run the equation and you get 50 as your equilibrium constant. Again, don't really try to understand. It doesn't have any units of measure. Don't try to understand too deeply what K means, what equilibrium constant means, other than the bigger it is, the more the reaction went from left to right, from reactants to products. The smaller it is, the more the reaction didn't go from left to right. It stayed as reactants and has very few products. This means the numerator containing the products is 50 times greater than the denominator containing reactants. That's kind of a loose interpretation, but again, you can see there's a lot of math involved there. There's a square up on the top. So to just say it's 50 times more products than reactants is really kind of a loose interpretation. Okay, there are several equilibrium constants we will be dealing with in the next few weeks. They are the equilibrium in a solution measured in molar concentration, so that's what the C stands for, is the concentration. The equilibrium of an equation of gas pressures, and those are treated mathematically, and the way you solve those problems is exactly the way as for concentrations. But it's K sub P, and that's for gas pressures. KSP is the equilibrium of a salt or other solid dissolved in solution. In other words, we often said that certain compounds, ionic compounds, would not dissolve or insoluble. Go to your solubility rules, and you will see you can see some of those. Well, the fact is there's nothing that totally doesn't dissolve. Little tiny pieces of something that we say is insoluble will actually dissolve. And so this is the equilibrium constant for how much of a substance that we say is insoluble will dissolve. And that's called the KSP. SP solubility stands for solubility product. KW is the equilibrium of water used in acid-base reactions. We'll be getting to that after Thanksgiving. Ka is the equilibrium of an acid reaction. It's called the acid dissociation constant. Again, that's coming after Thanksgiving. And Kb is the equilibrium of a base reaction. That's the base association. And again, that doesn't mean anything to you now, but it will after Thanksgiving. We'll be dealing with that. But you can see there's quite a number of different types of equilibrium constants that we deal with. The small letters are called subscripts. All equilibrium constants, large K, capital K, have subscripts. So let's look at and compare equilibrium constants to rate constants, because they kind of look the same, what we did in kinetics and what we're doing now in equilibrium. So the law of mass action comes from kinetic rate laws. Let's see how that works. Look at the decomposition reaction. N2O4 produces 2 moles of NO2. This is a reversible reaction that can move forwards and backwards. Each of these two reactions has its own rate constant. So you remember we did that when we did rate mechanisms. We took a reversible reaction and we said that it has a forward rate constant that's going from N2O4 over to 2NO2, and it has a reverse rate constant that's going from 2NO2 backwards to N2O4, and those are going to be different rate constants. So if we take the forward reaction, notice it's a one-way arrow. We're taking that reaction up above and we're only taking the left to right component of that. Then the rate equals the rate constant going forward of the reactant. We're only using a reactant here, N2O4. Now we're going to do the reverse reaction. We just flip the reaction around. Notice again it's a one-way arrow. So it has a different rate constant. So the rate of that equals the K reverse. That's the rate constant in the reverse direction, going from right back to left. And in that case, the reactant is the 2NO2 going in that direction, and which means in the rate law, you write it as NO2 to the second power. So those are the two rate laws. Now think about it. At equilibrium, what do you know about those two rates? If the amount of products and the amount of reactants are moving back and forth, but they're staying the same, what can you say about the two rates? These are both elementary reactions, so the coefficients can be used as exponents. When you break down a reaction like this, those are elementary reactions, so you can use the coefficients as exponents. At equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. So that's what I was getting at. The rates have to be equal if you're at equilibrium. The amount that's moving from reactants to products has to equal the amount that's moving back from products to reactants. So you can set those two rates equal to each other, and that's what you've done right here. So rearranging this reaction, K forward over K reverse, the forward rate constant over the reverse rate constant, equals NO2 squared over N2O4. And if you put those two K's together, that gives you the equilibrium constant. So that's how the equilibrium constant is derived from the rate constants. This means the equilibrium constant, Kc, equals the ratio of the rate constants for the forward and reverse reactions. The larger the value of Kc, the more the reaction moves in the direction of products, so from left to right. Large Kc means more of the reactants turn to products. Small Kc means more of the reactants stay as reactants and don't turn to products. Or if you started off with a large concentration of products and very little reactants, the reaction will move in the reverse direction to create more reactants from the products. Homogeneous equilibria means that all of the products and reactants are in the same state. So just a couple of simple generic reactions here. A plus B produces C plus D, and that's a reversible reaction. Everything there is aqueous, so that's a homogeneous equilibrium. In the second example, A plus B equals C plus D, all are in gaseous state, so that's a homogeneous equilibrium. Now, whenever a pure solid or a pure liquid, or a solid appear in a chemical equation, they are not included in the law of mass action. I'm going to read that a second time. Not that you're hard of hearing, but that you've got to remember that. Whenever a pure liquid, so the most common one, of course, would be water, H2O, or a solid, and there could be many of those, appear in a chemical equation, They are not included in the law of mass action. You do not need to understand why. You just need to remember that rule. So here's an example. So you have lead chloride. Now, our solubility rules told us that lead chloride is insoluble, but some of it will dissolve, very slight amounts will dissolve. So that produces a lead 2 plus ion, and notice what it doesn't produce, a Cl2 molecule. This is not a gas, it's not chlorine gas. That would be Cl2. This is in solution. So what it produces is 2 chloride ions. We talked about this principle some time back. So it's breaking into 3 different particles, a lead ion and 2 different Cl minus ions that are not attached or connected to each other in any way. So the way you would write this law of mass action is concentration of Pb2 plus times chloride squared. That's on the product side. That's over on the right side of the arrows. On the left side, the lead chloride is a solid. So normally that would go in the denominator of the law of mass action, but you don't put it there because it's a solid. So PbCl2, lead chloride, solid, does not appear in the law of mass action equation because it is a solid. Here we have hydrochloric acid being put into water, and it produces hydronium ions and chloride ions. We'll get into this equation after Thanksgiving. So there you see on the right side of the arrow you have the hydronium ion, H3O plus, and the chloride ion. On the bottom in the denominator you have the reactants, and that's the HCl. It's also H2O, but H2O is a pure liquid, so you do not put it in the law of mass action. H2O liquid does not appear in the law of mass action equation because it is a liquid. Equilibrium constants do not have units. Examples: write the equilibrium constants for the following reaction. So there you go. So go ahead. This is see if you can do this. You can maybe just do it in your head. You're going to end up with the equilibrium constant, and this is concentrations, is NOCl, and the coefficient of 2 in front of NOCl becomes an exponent. And then on the left side you have 2NO, so that becomes NO with an exponent of 2, and Cl2, and that has a coefficient of 1, so its exponent becomes 1. So you turn the coefficients into exponents. Do this one. Okay, what's on the right goes on the top, what's on the left side goes on the bottom. The only coefficient you see there is the 4, so it's going to look like that. So convince yourself, or be sure you understand why that is. Again, all the ion charges, don't let those confuse you. Those are ions. 2 minus, 2 plus, minus. Those are about ions. Those aren't about this particular concept of equilibrium. Let's do another one. Okay, there you have silver chloride. Your solubility rules tell you that's a solid in aqueous solution, so it's going to be solid. And then you have the silver ion and the chloride ion on the right, so what's the equation going to be? There it is. You do not include the AgCl in the denominator because it is a solid. Okay, and finally the reaction we saw before. And there it is. You do not include the water in the denominator because it is a liquid. So now we're going to compare the two because at the beginning, students can often get these confused. The rate law from the kinetics unit that we finished last week and the law of mass action from this current unit that we're in equilibrium. So let's take this reaction. Let's compare how the rate law would look versus the law of mass action. Okay, so on the left is going to be the rate law in blue, and on the right is going to be the law of mass action in red. So first of all, what's the purpose of each? The purpose of the rate law is to indicate the speed of the reaction. That's what we talked about last week. The purpose of the law of mass action is to determine the equilibrium concentrations of reactants and products. Where is that happy place that they're going to find where some reactants exist and some products exist and they kind of want to just stay there? Next, The rate constant for kinetics contains only reactants. It's only A and B. Only the left side of the arrow is included in the rate law, whereas the law of mass action in red there includes products in the numerator and reactants in the denominator. 3. Exponents are determined experimentally for an overall reaction. Remember, you can use coefficients if it's an elementary reaction, but if it's the overall reaction, you have to determine those using the table and experiments, and holding holding A constant to determine B and B constant to determine A. Okay, 3. For the law of mass action, exponents are the coefficients of each reactant and product because it consists of two elementary reactions, a forward reaction and a reverse reaction. Remember how we showed you that the equilibrium constant, capital K, was derived from the rate of the forward reaction being equal to the rate of the backward reaction. The forward and backward reactions, or reverse reactions, are both elementary reactions, and therefore you can use the coefficients as exponents, and that's what the law of mass action does. 4. The rate constant is a lowercase k, the equilibrium constant is an uppercase K, and always has a subscript, A, B, C, P, S, P, and W, that we talked about in a previous slide. 5. The rate constant is part of the rate law equation used to compute the rate of the reaction and appears on the right side of the equation. For law of mass action, the equilibrium constant is the output value of the law of mass action used to determine the equilibrium values of reactants and products, and appears on the left side of the equation. So just look where the K's are in each of those equations. 6. The units of measurement for the rate constant depend on the order of the reaction. So K has unit of measure depending on whether it's 0 order, first order, second order. K will either be 1 over seconds, 1 over molar seconds, or something else. On the right side, the equilibrium constants do not have any units of measurement. Capital K on the right side does not have units of measure. And on this slide, there's a summary of the six differences that we mentioned on the previous slides. If you want to take a screenshot of this, you can do that. Okay, there are equilibrium constants for equations expressed in terms of gas pressure rather than concentrations. So there's an equation, there's the law of mass action in terms of Kp. That's the equilibrium constant using gas pressures, and that's the way you would write it. Simply write the pressure of whatever the reactant or product is, and then raise it to the exponent, and you use parentheses, not square brackets, when you're dealing with pressures. Using the ideal gas law, PV equals nRT, an equation relating Kp to Kc can be derived. You should know the equation, but not how to derive it. So there it is right there. And the way you learn it is you can just memorize that. So the equilibrium constant for pressure equals the equilibrium constant for concentration times R, that's the gas constant, times temperature in Kelvin, and it's raised to the power of change in number of moles. So let's look at that equation up above. You have 2 moles of A and 3 moles of B producing 4 moles of C and 5 moles of D. Now this is just a hypothetical reaction, but on the left side of the arrow you have 5 moles total. A and B, if you add the moles of A and B together, it's 5. If you go over to the right side and add the moles of C and D together, it's 9. So that would be a change in the number of moles of 4. You went from 5 up to 9. That would be a change of plus 4. If you decrease the number of moles, then that would be a negative number. So change in number of moles can be a negative number. Okay, and if you solve that for Kc, then there you see what you would get right there. Okay, if you just memorize one of the equations, you should be able to use algebra to get to the other one. And R in this case, the gas constant, is the 0.0821 liter atmospheres over mole Kelvin. T is measured in Kelvin, and delta N is the change in the number of moles. Okay, so let's take an example here of N2O4 in a reversible reaction to produce NO2, 2 moles of NO2. We're given a equilibrium constant, pressure constant of 0.256 at 25 degrees centigrade. It says consider the calculation for the conversion of Kp to Kc. So what is the temperature used? First of all, you got to convert to Kelvin. Don't forget to do that. And if you're ever in doubt in chemistry, you pretty much always convert to Kelvin if you're not sure. So that would be 298 Kelvin. What is the value of R? So you want to use 0.0821 liter atmospheres over mole Kelvin. Don't use the other value of R. That's the 8.21 joules per mole Kelvin. I believe that's 8.31, so that's a typo. What is the value of N? There is 1 mole of reactant and 2 moles of product. So if you look up there, N2O4, there's 1 mole, and over on the right side, there's 2 moles of NO2. So therefore, that's an increase of 1 mole. So delta N equals plus 1. D, what is the value of Kc? Okay, so to do that, there's Kc. So you just go ahead and plug in what you have there. And don't worry about units of measurement canceling here. It's a little bit strange. Just understand that Ks don't have any units of measure. An equilibrium constant, whether it's Kc or Kp, doesn't have any units of measure. So you're simply going to come out with Kc equals 0.01. So that's simply something you may have to do sometime, is convert between the equilibrium constant for pressure and for concentration. Okay, here's another example. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472 centigrade. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of H2, 2.46 atmospheres of N2, and 0.166 atmospheres of NH3. From these data, calculate the equilibrium constant for pressure, Kp, for the reaction. Okay, so there's the reaction. So there would be the rate law. So what you would have to do is first is write the equation and then balance it. Okay, so that wasn't done for you in this problem, and they could expect you to do that on an AP problem. So if you do that, N2 plus 3H2 gives you 2NH3, so that's the balanced equation. So now you can write the law of mass action. The product goes on top, NH3, and it's to the second power. The reactants go on the bottom. They're multiplied, and for H2, it has a coefficient of 3, so it's to the third power. So now you can simply plug in those concentrations, and that will come up with Kp, which is 2.79 times 10 to the negative fifth. Again, no units of measure on a equilibrium constant. An equilibrium constant does not have any units of measure. So equilibrium follows a few basic mathematical rules. Now you remember when we did Hess's law, we had some rules. If you multiply an equation by 2, then you multiply the enthalpy by 2. If you reverse the reaction, then you change the sign. These look like that in a way, but they're totally different. So don't get these confused with the rules for what you do when you do use Hess's law. So rule 1, when a chemical equation is reversed, the equilibrium constant becomes the reciprocal of the original constant. Again, don't think too hard about why this is. Just learn these rules, and the best way to learn them is just by practicing a number of problems, okay? So here we go. If you have A plus B produces C, and let's say that the equilibrium constant is 2, if you flip that reaction around, C produces A plus B, you take the reciprocal of 2, 1 over 2. So it's not like Hess's law where you'd put a negative sign in front of the 2. That's not it at all. You take the reciprocal. Okay, rule 2, when a chemical equation is multiplied by a factor, a number, the equilibrium constant is raised to the power of the factor. So example, if the reaction below is multiplied by 2, then the equilibrium constant is raised to the second power. So if we go ahead and multiply that reaction, 2A plus 2B produces 2C, then you take that original equilibrium constant of 3 and you raise it to the second power. And that means the equilibrium constant would be 9. And rule 3, when two equations are added, then the equilibrium constants are multiplied. So here we have an equation, A produces B, and the equilibrium constant for that is 2. Here we have C produces D, and the equilibrium constant for that reaction is 3. If we add them together so that we get A plus C produces B plus D, then what you do is multiply the two equilibrium constants, 2 times 3, and that gives you 6. So they are totally different rules than for Hess's law. And that takes care of this lesson, first lesson on equilibrium.